Let's look at the third test in this lecture. The third test is the comparison test, or sometimes we call it the direct comparison test, because as we'll see in the next lecture, there's another test, it's called the limit comparison. In order to use this test, we need to ensure that the terms an are all positive. Then we are going to find another series with terms bn, where bn also have to be positive terms. Then, if we can show that for all the terms, an is smaller than bn, and the series of bn is convergent, then it's intuitive that the series an is also convergent. Since all the terms compared to bn, an is smaller than bn. So if sum of bn is convergent, then sum of terms which are smaller than bn should also be convergent. And the second conclusion is also intuitive. If we can find a second series with terms bn, where an is always greater than or equals to bn for all n, and if the series of bn is divergent, then the series of an should also be divergent. Since the sum of bn is divergent, and the series with terms an, where all the terms are greater than bn, then its sum should also be divergent. And similarly to the integral test, as long as we can find a value such that an is always greater than or equals to bn, or an is always smaller than or equals to bn, then that is sufficient to use this comparison test. And when do we use this test? There are two hints. First, if an is a rational function or an algebraic function of n, then we can compare the series to a p-series or a geometric series, where we can quickly determine whether the series is convergent or divergent. And the second hint is when we know the range of a series. A common case is when we have cosine function or sine function. Since we know that a sine function and a cosine function, they are always bounded between -1 and 1. So when we know the range of an, then that is also a hint to use this comparison test. Let's look at the first example. Determine whether the series sum of cosine square of n divided by 1 plus n squared converges or diverges. So for this series, we have an, which equals to cosine square of n divided by 1 plus n squared. In the numerator, we have cosine square. In the denominator, we also have the square for n, and we have plus 1. So an are always greater than 0 for all the n's. In a quick recall, we just mentioned that cosine function and sine function, they are bounded between -1 and 1. So if we take the square on both sides, we get that cosine square is always smaller than or equals to 1. Then we can let another series with terms bn, which equals to 1 over 1 plus n squared. So for all the n's, an is always smaller than or equals to bn. Since we can compare the numerator, an is cosine square and bn is 1. And we just showed that cosine square is always smaller than or equals to 1. If we can show that the series bn is convergent, then sum of an should also be convergent. We can use the integral test. Since the function for bn is positive, decreasing, and continuous for n that is greater than 1. So we are allowed to use the integral test. Let's compute the improper integral evaluated from 1 to infinity of 1 over 1 plus x squared. We know that the antiderivative of this function is arctan, and if we substitute the upper bound and the lower bound, we get that this integral is convergent. So, the series of bn, sum for n starting from 1 of 1 over 1 plus n squared is convergent. So we proved that the series of Bn is convergent, and since all the terms from the first series, An is always smaller than or equals to Bn. So if sum of Bn is convergent, then by the comparison test, the series for An should also be convergent. So the sum for n starting from 1 of cosine squared divided by 1 plus n squared converges. Now let's look at the second example. Let's determine whether the series converges or diverges. Here we have the An, which equals to 5 divided by 2n squared plus 4n plus 3. If I remove the plus 3 in the denominator, then the term will be greater than An. So this is smaller than 5 divided by 2n squared plus 4n. While if I remove the 4n, then this would be smaller than 5 divided by 2n squared. So let's let Bn be this term, 5 divided by 2n squared. Then what's the sum of Bn? Sum of Bn for n starting from 1, which is the sum for n starting from 1 of 5 divided by 2n squared. I can factor out the constant. This equals to 5 over 2, then the sum of 1 over n squared. The sum of 1 over n squared is a p-series with p equals to 2, which is greater than 1. So we know that this is a convergent p-series, which means the series of Bn is convergent. And since all the terms An is smaller than Bn, so we have sum of terms which is smaller than a convergent series, then by the comparison test, this series, sum for n starting from 1 of 5 divided by 2n squared plus 4n plus 3 also converges. And let's look at the last example for this lecture. Let's determine whether the series sum of ln of k divided by k converges or diverges. So for this series, we have the terms ak, which is ln of k divided by k. This term is greater than 1 over k for ln of k that is greater than 1, which also means when k is greater than e. Now let's let a second series with terms bk equals to 1 over k. And we know that the series of bk is a p-series with p equals to 1. So this is a divergent p-series. And since for terms where k is greater than e, we have ak is greater than bk. So if sum of bk diverges, then by the comparison test, the series for ak, which is the sum for k starting from 1 of 1 of k divided by k, also diverges. And that is the end of the lecture. In the next lecture, we are going to look at the fourth test, the limit comparison test.